All right, hey, one last example using this natural law of growth and decay. And that's money in a bank. And banks will give you interest, say, in a savings account or a money market account in two basic ways. One is called compounded interest, and one is called, well, where the interest is compounded, was called continuously. Um, the idea of compounding money works as follows. So let me give you an example. Let's suppose that the bank says that they're going to give you an interest rate of, and I'm just obviously just picking arbitrary numbers here, but let's say the interest rate is 7%, so 0.07, and I could have said 7/100ths, and it's per year, but the money's compounded, um, compounded daily. That's going to be a key thing. What on earth does that mean, compounded daily? And just to make the numbers really, really easy, um, let's just say that the initial amount you invest is, I mean, I could really make it anything, but I just want to make the numbers really easy. Let's just say $8. Here would be a typical question. How much money would you have after 1 year? So the bank's going to give an interest rate of 7% compounded daily. And you initially invest $8. You come back a year later, what would you have? If you took 7% of 8, that's and added it to 8, that's not what you would get. I mean, it would be close in this case, but it's not what the banks do. So what do the banks in fact do? Well, I'll show you. How much would you have after 1 day? Just consider 1 day. What would the amount be after 1 day? Well, it would be your initial amount plus the percent of that. But you don't get 7% because you only left it in for a day. And this was 7% per year. So in fact, what you have here is 7%. This is all divided by, let's just say there's 365 days. There's leap years, right? But now I want to do something with this mathematically, which is not obvious. So it's a little bit like we're in a wilderness area and you're not familiar with it. And I say, well, at this mossy rock, we're going to turn left. And your question is obviously, how did you know to go left? And the answer is, because I've lived here for a long time and I've explored all around and I know this is what to do. So the tempting thing to do would be to throw that in your calculator, but that's exactly what you don't want to do. What we want to do is factor the 8 out, and what we're left with is this. That seems like a strange thing to do, I admit, but just follow along here. How much would you have after day 2? Well, this is what you have at the end of day 1, so that's what you start day 2 with. But then you earn, again, 1 day's interest on what you started the day with. So what does 1 day's interest look like? 0.07 divided by 365, just still on the screen barely, times what you started the day with. Okay, so again, what is this? What does this all represent? It's what you started the day with plus 1 day's interest on that. Now I can factor out this. Those two things are the same. And if you factor those out, what would you be left with? Well, you factor this out. Remember the reverse of the distributive rule. And what you'd be left with is this. Let me write this down and I'll get out of the way. And then you notice that these two things are the same. So where should I write it? Let me write it over here. The amount after day 2 is equal to this. Now let me go back. This is after day 1. And as a matter of fact, watch this. How much did you start with? Because anything to the power 0 is 1. Well, now you see the pattern. To start with, kind of day 0, if you will, after 1 day, after 2 days. So we can see now that the pattern looks like this. Let me erase this here. I need to wash this board down again. The amount of money that you have after D days is equal to, I was jumping to the conclusion here. There is a conclusion that we're getting to here, but it's this. Now that works for this particular case, but what I'm aiming towards is to get a formula that works in all situations. Well, where did the 8 come from? That was the initial amount. What's up with this 0.07? Well, that's the interest rate. Again, like I keep saying a million times, but you can use whatever letters you want. I'm using R for interest rate and A for amount. Okay. Now, how much money would you have after 1 year? Well, how many days in a year? This would be 365. What about 2 years? 2 times 365. What about 3 years? 3 times 365. How much money would you have after a given number of years would be the initial amount plus this. Now, the final thing I want to replace here is this 365. I mean, how did 365 work its way into this problem? It's the number of times per year that the money is compounded. So I can replace this. Here, maybe I'll put an N for the number of times the money is compounded. Now this is the actual formula that banks use when they compound interest in this way. I mean, it was quarterly, that would be 4 times a year, monthly, 12 times a year, biannual, twice, whatever, do it a million times a year. Now, what I suggest you try doing, and I'm not going to do here, but I really do suggest you try doing this. Let me erase this here. I'll leave that formula up. Is use this scenario right here. Let's say the initial amount of money is 100, and let's say the interest rate is 7%. 100 will make it, for what I'm about to ask you to try doing, 100 will be a kind of a nicer number to deal with. Let's let 1 year go by. So this is 100. This is 1. This is 0.07. Get out a calculator and calculate what you get where n is equal to 1, 2, 3, 4, so on and so forth. Oh, I mean, what do you do for, and then how about maybe skip to 10, 50, 100, 1,000, 1,000 times a year, about 3 times a day. And then, maybe even try 1,000,000. And you will notice a pattern, and you will notice something interesting if you do these calculations. What you'll notice is that you will make more and more money, but there seems to be a limit, and there is. There'll be a maximum amount of which you can't get beyond. Now, I can't exactly tell without doing these calculations. I mean, imagine, say n is even just 100. That would be about every 3 days. What would you have to calculate? Well, you'd have 100 up here. I mean, this you could do, fine, 0.07 divided by 100, 0.0007, add a 1 to it, 1.0007. But you'd have to raise that to the power of 100. That means you'd have to take that number and multiply it by itself 100 times. There's no way I can do that in my head, or anybody can do that in their head. I can maybe make a rough kind of estimate, but I certainly can't do the calculation. But a computer, boom, calculator, do it like that. Now, hopefully you do that. Hopefully you accept that challenge. I have to say, that's the kind of thing that it's good to do once in your life. There's no point in ever doing it again. It's like a one-time thing only. This formula, I see no reason why you should memorize it. It's good to know it exists. There it is. But what happens that's interesting is the following. If you make n large, By large, I don't mean a million. It's not enough. A billion, more. A trillion, more. How about a trillion times a trillion times? Trillion raised to the power of a trillion. More. I can't say make n infinite because infinity is not a number. There's different sizes of infinities, and I don't want to go down that road right now. We'll save that for advanced calculus or analysis. But if you make n really, really large, and then you add, I'm going to say a bit of magic. It's not magic, it's actually calculus. But for right now, it might as well be magic. So if you make n very, very large, say a trillion raised to the power of a trillion, and then you do a little extra additional mathematics, this formula becomes something else. And it becomes this. And again, this I showed you why it is what it is. I mean, did it fairly quickly, but I showed you why this is what it is. I'm about to write down what this becomes, and now I'm not justifying this. I'm saying take my word for it. If you want to know why, again, get to calculus, boom, and you'll find out why. But it becomes this. Our old friend, the natural law of growth and decay. So this is yet another example. I would show you radioactive isotopes, elimination of drugs in a body, growth of bacteria in a petri dish, now money in a bank. There's thousands of others. I don't even know how many there are. And what does this mean when it comes to money in a bank? This is what you initially invest. This is what you end up with after Y. Well, Y is a period of time. It doesn't have to be years, but probably most conveniently with banks, it is years. R is the interest rate. So R is the interest rate. So when it comes to banking, remember when it's radioactive isotopes, this is called the decay constant. When it's bacteria in a petri dish, it's called the growth rate. When it's drugs in a body, it's called the elimination rate. When it's money in a bank, it's called the interest rate. So just sort of a really quick problem here. And I think you get the idea now. We've done a bunch of these. But let's suppose I initially invested, who cares, $1,000. And let's suppose I have a financial goal, and I say to myself, well, in 20 years, I want this to be worth 5,000. It's my financial goal. What interest rate would I have to get to achieve that goal? Well, let's throw everything in this equation. So the amount after 20 years, our goal is 5,000. And the initial investment is 1,000. E to the, we don't know the interest rate. That's what we're going to solve for. And T or Y or time, but in years is 20. So we'll solve this for R. Now the good thing is we solve this for R just like we did on all the other examples here. So let's divide both sides by 1,000. Take the natural logarithm on both sides. That cancels with E. Divide both sides by 20, and we get this. And we throw that in our calculator, and that's the answer to our question. Okay, so the natural law of growth and decay, it may seem like I spent a lot of time on it, but you really can't spend too much time on it. If you take more math classes, you'll do more and more and more things with it. I was going to do something with this, which is a modification of this called the logistics equation, which is used to analyze population growth. I mean, I talked about bacteria, but bacteria, like I said, if you keep them happy, but they're not always happy, they eventually poison themselves and run out of room and run out of nutrients. But we'll just leave it at this. We'll not go down that road. And so the test Friday is going to cover everything in chapter 10. So I think I'll go and I'll make a review kind of video of all the concepts of chapter 10 tomorrow. And let me know if you have any questions.